So let us begin with this next chapter, that is dual nature of matter and radiation. This is an interesting chapter. Okay. All right. So let's begin with this. So consider this metal wire. Now, what's there inside the metal wire? So metals are generally made up of atoms, right? So inside atoms there is a nucleus and there are electrons. Okay, we know that. So atoms of metals, they gain sufficient energy from the surrounding at room temperature only, and the electrons in the atoms, they become free. And that's why what happens is, if you consider a piece of metal or wire of metal, there are lots of electrons, they are moving in random directions. Okay, so electrons are free, they are moving in random directions inside the metal surface only, right? So now you might ask, if electrons are free, why don't they come out of metal surface? So reason for that is, the electrons are still in a positive potential. Okay, in a positive potential, because see, if an atom loses an electron, the atom will have a positive charge. So there are numerous atoms there, okay, millions of atoms which have a positive charge. So that positive charge of atoms, okay, electrons are surrounded by these atoms, right, which are positive charge, you can call them ions. So that's why the electrons don't have sufficient energy to come out of metal surface. Okay, so electrons are out of the atoms, they are randomly moving inside the metal surface, okay, but they don't have sufficient energy to come out of the metal surface, okay, to overcome the potential barrier due to these positively charged atoms, you can say. So now you can give them this energy in several ways. So what you can do is, see, the electrons, they are moving in the metal surface, okay, the energy that they require, the minimum energy required by electrons to escape from the metal surface, this is known as the work function. Okay, this energy is known as the work function. Now you can give that energy in various ways. So depending upon the way that you provide the energy, the emission of electron from the metal surface, it is defined in that way. Okay, so thermionic emission. So if you heat the metal surface, the electrons may come out of metal surface if they gain sufficient energy. Okay, so thermal energy is imparted to electrons to enable them to come out of the metal. So this emission is known as thermionic emission. So next, what you can do is, you can apply some electric field, right? So when you apply an electric field, that means you have some positive potential, let's say positive potential, so electrons will get attracted by a positive potential. So they might gain sufficient energy if the potential is sufficient. Okay, so this is called as field emission. If you apply some electric field, this is known as field emission. And then there is photoelectric emission. So what you can do is, you can just strike this metal surface with the light, okay, or the electromagnetic waves, you can say. Okay, so when light of suitable frequency illuminates this metal surface, the electrons are emitted. So this is known as photoelectric emission. Okay, is this thing clear, everyone? All right. So after that, let us talk about the Hertz and Lenard's experiment. Okay, so Hertz and Lenard were two physicists who worked on the photoelectric effect. Okay, that is the photoelectric emission of electrons, and they observed some strange things which couldn't be explained by the classical theory of light. Now, what is classical theory of light? So we know that light is made up of waves, and that it is made up of the electromagnetic waves. So this is called as classical wave theory of light. Okay, and we also talked about the Huygens theory, right? So Huygens theory is wave theory of light, and Huygens didn't know what kind of wave light is made up of. So it was proved later by Michael Faraday, Maxwell, that it is made up of the electromagnetic waves, and that is known as the classical electromagnetic wave theory of light. Okay, so there are some observations which couldn't be explained by that theory. Okay, so we'll talk about that. All right, so see, the experimental apparatus of Hertz or Lenard's, it looks something like this. This is the schematic diagram. So this is a glass tube. Okay, this is evacuated glass tube. There is a vacuum inside this glass tube, and here you have a source of light. Okay, so Then there is a quartz window over here so that the light will enter in this tube. Okay, and there is anti-reflecting coating also, so that the light will only enter and it will not get reflected back. Okay, then there is a photosensitive metal plate. So what's that photosensitive metal plate? So here the light will strike on this metal plate. It's photosensitive means then when light strikes, the electrons will come out. Okay, and then you apply some potential difference. So this is known as the cathode. Okay, and this end is known as anode. So you apply some potential difference between these two plates. So some battery is connected over here. Okay, so sometimes this is given negative potential, this one is given positive potential. Sometimes the potential difference between them is zero. Sometimes this one would be given positive potential, this one would be given negative potential. Okay, so we'll talk about that. All right, so the C is the emitter or it is the cathode. Emitter means it will emit electrons. Okay, A is anode or it is also known as collector, right? So now we need to remember one thing, that intensity is inversely proportional to R square. So if you move the source of light away, then what will happen? The intensity will decrease. If you move the source of light closer, then what will happen? The intensity would increase. Okay. So now see, what are the experimental observations of Hertz and Lenard? So they observed, see this first graph, the photocurrent versus frequency. Now what is photocurrent? See, the electrons will be emitted by this metal plate, then it gets collected by this anode. Okay, the electrons are emitted by the cathode, they get collected by the anode, and then you connect some ammeter to it. Okay, ammeter in this circuit, right? So when you connect an ammeter, it will measure some current. Okay, so that current is called as photocurrent. Why photocurrent? Because the electrons are emitted because of what? This is photoelectric emission. Okay, that means you incident this metal surface with light and electrons come out. So this is photoelectric emission. Okay, so that's why this current is known as photocurrent. So see here, the photocurrent and frequency, the graph between them, it's like this. Okay, that means until certain frequency, certain frequency, there is no photocurrent. Okay, whatever is the intensity of light, whatever is intensity of this light, till the time the frequency is less than this particular frequency called as threshold frequency nu naught, there is no photocurrent. Okay, no matter how much is the intensity, how big is the intensity. Okay, so then after this frequency, what happens? The photocurrent, it gets quickly saturated. Okay, it gets quickly saturated. Here intensity is kept constant. So as you increase the frequency, there is no change in photocurrent. The photocurrent quickly saturates. Okay, see the next graph. Next graph is between the photocurrent and the intensity. So here you fix some frequency greater than this one called as threshold frequency. So if the frequency is greater than the threshold frequency, then the photocurrent is just directly proportional to the intensity. Okay, photocurrent is just directly proportional to the intensity. Okay, this is the second graph, right? Next one. Now next one, to understand next one, now what do we need to do? We need to apply some potential difference here. Now you can see this graph, when potential difference is positive, that means the anode is at higher potential, cathode is at lower potential. Then what happens? As we have seen the last graph, this one, okay, at any frequency greater than nu naught is the threshold frequency, the photocurrent is directly proportional to intensity. That means if you increase the intensity, the current will increase. So what you do is you choose a particular frequency nu greater than nu naught and you just change the intensity. Okay, so you choose intensity I1, I2, I3. I3 is greater than I2 is greater than I1. So obviously you will get more current for larger intensity. Okay, you choose different intensities I1, I2, I3. I3 is greater than I2 is greater than I1. Frequency is constant. Frequency nu is greater than nu naught, right? Nu is greater than nu naught. So we have seen that photocurrent is directly proportional to intensity. So if intensity is greater, the current will be more. So current for I3 is greater than current for I2, and it's greater than current for I1, right? But then now when you apply negative potential to the anode, positive potential to cathode, now what will happen? See, the electrons that are coming out of here of the cathode, they will be opposed by the anode, right? Because you have applied a negative potential there. So they are opposed by the anode, and therefore now what will happen? Their speed will decrease. So now if you crank up the potential difference, that means you increase the potential difference here. So you apply more and more energy to decrease the kinetic energy of electrons. So there will be some point where the electrons will stop. Okay, so that means at some value of the negative potential difference applied to this anode with respect to cathode, the electrons will stop. So that is known as a stopping potential. Okay, that is known as a stopping potential, right? So electrons, they stop at the same potential. Okay, that means current becomes zero. How will you know that electrons have stopped? They are not coming, they are not reaching the anode. The current will become zero. Okay, if some electrons reach the anode, there will be some current flowing through the ammeter connected to this anode, okay, or this side of the circuit, right? So if electrons stop, there will be no current. Okay, this thing is clear, everyone? And the observation here is, no matter how much was the intensity of this light, okay, how bright was the light, how much was the intensity of light, the electrons will stop at same potential difference. That means, so see here, the stopping potential for intensity I1, I2 and I3 is equal. What does it mean? It means that whatever is the intensity of light, how bright is the light, it doesn't matter. If frequency is same, if you don't change the frequency, don't change the color of light, okay, you just change the intensity, then the electrons stop at same negative potential of the anode. Okay, what does it mean? You need to apply same energy to stop electrons, and if you apply same energy to stop electrons, that means electrons have same amount of energy, or these electrons will have slightly different energy. Okay, some electrons will be little bit faster, some will be little bit lesser, but maximum kinetic energy of electrons would be same, because you need to apply the same negative potential over here. Is this thing clear? So if maximum energy of electrons is same, that means the energy that they are getting from light is also same, and it does not depend on the intensity. Okay, if energy you need to apply to stop electrons is same in all three cases for intensity I1, I2, I3, that means energy of electrons does not depend on intensity. Energy the electrons are getting from light does not depend on intensity. Okay, so next what you do is, you keep the intensity same, you change the frequency. That means the brightness is same now, okay, for different frequencies. Okay, so this nu3 is greater than nu2 and it's greater than nu1. So frequencies are different, intensity is same, and then if intensity is same, as you have seen here that photocurrent is directly proportional to intensity. So for different frequencies you get same amount of photocurrent. Okay, if collector potential is positive, okay, if anode potential is positive, then now if you make this make the potential negative, now how much potential difference you need to apply to stop these electrons, it will be different in different cases. Okay, so the stopping potential is different in different cases. See here, the stopping potential is different in different cases. So for nu3 the stopping potential is this much, for nu2 the stopping potential is this much. Okay, for new one the stopping potential is this much, right? So for light having greater frequency, if electrons are incident with the light with greater frequency, then the stopping potential for those electrons is greater. What does it mean? Electrons are moving with more kinetic energy, that's why you need more stopping potential, right? So it means that the energy of electrons increases with the frequency of light. Okay, if you shine this metal surface with a light of higher frequency, then the electrons gain more energy, and that's why the kinetic energy will be more, kinetic energy of electrons will be more, right? So that's why you need more stopping potential to stop those electrons. Okay, so this observation says that the energy of electrons increases with what? It increases with the frequency. Okay, all right. So see, what are the observations? So first one, no photoelectric current is observed till frequency of incident light nu is greater than nu naught. So this was your first graph. Okay, so whatever is the intensity, electrons don't get the required energy. Okay, what does it mean? Unless the frequency hits nu naught, whatever is the intensity, the electrons don't just get the required energy. Okay, so this first graph tells you that energy does not depend on the intensity. Energy of the light does not depend on intensity, or at least energy that electrons gain from light does not depend on the intensity. Okay, second graph says that nu is greater than the threshold frequency. So at a particular frequency of light called as nu naught, the electrons come out of metal surface, right? So if nu is greater than the threshold frequency, after that the current is directly proportional to intensity. That is your second graph. Okay, so now you increase the intensity, current increases means the number of electrons that are coming out per unit time of the metal surface, it increases. This is the second graph, observation from the second graph, right? Then third graph. So what does the third graph say? Again, so you have seen the current is directly proportional to the intensity. We are using I for intensity. Okay, so as the intensity increases and the potential of this anode is positive, then you get more current. You get what? More current. Okay, but if you make the potential difference negative, then what happens? Then frequency is same here and just intensity is different. So for all cases, that is I1, I2 and I3, the electrons stop at the same potential. That means the energy that electrons get from the light is same in all three cases, no matter how much is the intensity, because we require same amount of energy to stop the electrons, same amount of stopping potential to stop the electrons. That means the maximum kinetic energy of electrons is same in all cases, no matter what is the intensity, if frequency is same, right? So that is the third observation. Right? So if nu is equal, V naught is same for all intensities, that means energy of electrons is same. Okay, and observation number 4, if you change the frequency and keep intensity constant, you choose different light, okay, and keep intensity constant, intensity same, then the stopping potential changes. If frequency is more, stopping potential is more. If frequency is less, stopping potential is less. That means electron gain more energy from the light if frequency of light is more, right? So these are the observations so far. So now let's understand what do these observations imply. Okay, so from this graph, what can we understand? Now see, the electrons will have some kinetic energy. Okay, electrons will have some kinetic energy. The maximum kinetic energy of electrons, they will have slightly different kinetic energies. Some will be a little bit slower, some will be a little bit faster, but they will have some kinetic energy. and you are stopping all of them. So that means the maximum kinetic energy of electrons would be equal to what? It would be equal to work done by the stopping potential, work done by the electrostatic potential. Okay, so the maximum kinetic energy of electrons must be equal to what? Work done by the stopping potential to stop electrons. Okay, so the work done by stopping potential is equal to charge on an electron multiplied by the potential difference. Okay, that is the work done by electrostatic potential difference. All right, so therefore we get this formula Ke max is equal to EV naught, and then Ke max is half of m is mass of electron multiplied by V max square. What is V max? It's the maximum speed of electrons. Okay, it's the maximum speed of electrons, right? Then the minimum amount of energy required by an electron to come out of a metal surface is known as the work function. It's known as what? Work function, and we will denote it by phi naught. Okay, so just remember that. So now let's talk about the characteristics of photoelectric effect. So the photoelectric effect has the following characteristics. The current I is directly proportional to, so these are just observations. Okay, the current I is directly proportional to the light intensity. Okay, if light intensity is doubled, the current also doubles. Okay, the current appears without delay. So this is important. Current appears without any delay. Photoelectric effect is spontaneous. So light is incident on the photosensitive material and the electrons come out. Okay, it's that fast, right? The electrons are emitted only if light frequency f exceeds the threshold frequency f naught, or we are calling it nu and nu naught. Okay, and the value of threshold frequency depends on the type of metal. So this threshold frequency is different for different metals, okay, from which the cathode is made. So nu naught is different for different metals. Okay, because you can imagine that electrons will be surrounded by different kinds of atoms, different kinds of ions. Okay, and density of those ions in the surrounding will also be different. That's why they will need different amount of energies to come out of different kind of metals. Okay, so that is like a common sense. Okay, all right, so now what do we expect from the wave theory of light? So this is important. What do we expect from the wave theory of light, and how our expectations are not matching with these observations? Okay, so photoelectric effect must not be spontaneous. Why it shouldn't be spontaneous? See here, so suppose this is a wave. Okay, it strikes with an electron. So now the energy of wave is not localized at one place. It's not a particle, it is a wave, right? So some amount of energy is here, some energy is here, some energy is here. So if wave is spread, let's say in 50 kilometers, then the energy of wave is spread in 50 kilometers, right? So if wave strikes with an electron, the electron doesn't immediately get all of its energy. It can't get all of its energy. So the electron has to be illuminated by light for sufficient amount of time so that it gains some energy. It gains sufficient energy to come out of metal surface, and that's why the photoelectric effect must not be spontaneous. Okay, because energy of wave is not localized. This is the first observation, and it doesn't match. It doesn't match with our classical wave theory of light expectation. Okay, our expectation from the wave theory of light. Okay, then there shouldn't be any dependence with the frequency. There shouldn't be any threshold frequency. Why shouldn't be? Why the threshold frequency shouldn't be there? Reason for that is, see, we know that energy or the intensity of light is directly proportional to amplitude square. We have seen this in the wave theory of light. So now if you increase the amplitude, the electrons must get sufficient amount of energy no matter what is the frequency, right? If you increase the amplitude, the electrons must get sufficient amount of energy no matter what is the frequency. Yes, no, this was our another expectation. Okay, whatever is the frequency, brightness is enough, electrons should come out. But that's not happening. Electrons are not coming out before uh, a fixed frequency. Okay, if frequency is less than this much frequency called as threshold frequency, electrons are not coming out. That means they are not gaining sufficient amount of energy. So this is also not matching with our expectation. Okay, and electrons must get required energy if the intensity is increased enough. Okay, so that's the same thing. Okay, so that means using the classical wave theory of light, you cannot explain the photoelectric effect. Okay, you cannot explain the photoelectric effect. Is this thing clear, everyone? So then let us discuss some problems just based upon this much theory. Okay, then we'll come back to the problem of the photoelectric effect. Okay, let's see this one. A source of light is placed at a distance of 50 centimeter from photocell and stopping potential is found to be V naught. If distance between the light source and photocell is made 25 centimeters, the new stopping potential will be. Tell me. You are not changing new. The frequency of light is not changed. Okay, so it's option B. Very good. It's V naught only. Okay. If you change the distance of source, what changes? The intensity changes. Frequency does not change. Okay. So intensity changes. Intensity depends on distance and not the frequency. Not the frequency, and therefore the stopping potential does not change. Okay, stopping potential is independent of intensity. Okay, stopping potential is independent of intensity. Right, so very easy question. Stopping potential is independent of intensity, and by changing the distance you can only change the intensity, right, not the frequency. Okay, and therefore the stopping potential will not change. All right, let's see next one. The photoelectric emission occurs only when incident light has more than certain minimum. Tell me. Power, wavelength, intensity, frequency. Very simple question. All right, so it's option D. Okay, everyone knows this. Okay, let's see next one. In photoelectric emission process from a metal of work function 1.8 eV, the kinetic energy of most energetic electrons is 0.5 electron volts. Okay, so what is work function? Work function is minimum amount of energy required by the electrons to come out of metal surface. Okay, so that's work function, the minimum amount of energy required by electrons to come out of the metal surface, right? So in photoelectric emission process from a metal of work function 1.8 electron volt, the kinetic energy of most energetic electrons is 0.5 eV. Okay, electron volts. The corresponding stopping potential is. Okay, so now we know the relation between kinetic energy and stopping potential. Okay, so here actually we have seen this unit earlier also. What is electron volt? 1 electron volt. If 1 electron is accelerated by a potential difference of 1 volt. Okay, so it is energy of electron accelerated by potential difference of 1 volt. And how much that energy would be? So we know that energy would be equal to charge multiplied by potential difference. Okay, charge on an electron is 1.6 multiplied by 10 raised to minus 19 coulombs, and potential difference is 1 volt, and therefore it is equal to what? 1.6 into 10 raised to minus 19 joules. Okay, 1 electron volt is just equal to what? 1.6 into 10 raised to minus 19 joules. So we need to remember this unit. Okay, so then what is kinetic energy? It's 0.5 eV, right? So it's given that Ke is equal to 0.5 eV, and we know that Ke would be equal to what? E multiplied by V naught. We have seen this formula. So this is equal to 0.5 in electron volts, and it's equal to E multiplied by V naught. This is given. So just convert electron volts to joules. How will you convert it? Just multiply it by charge on electron. So 0.5 multiplied by E, we can say, is equal to E times V naught. So that E will get cancelled out. So you will get V naught is equal to 0.5 volts. Right? So that's very simple. It's option C. This is clear. When monochromatic radiation of intensity I falls on a metal surface, the number of photoelectrons and their maximum kinetic energy are N and T respectively. If the intensity of radiation is 2I, the number of emitted electrons and their maximum kinetic energy are respectively. Tell me. When monochromatic radiation of intensity I, option B, 2N and T. Very good, that's correct. Right? So what is intensity, or what's the relation between current and intensity? Current is number of electrons coming out per unit time, right? Or current is directly proportional to electrons coming out per unit time. Okay, so if you increase the intensity, current will increase. We know that it's directly proportional to current, and that means if you double the intensity, the current will double. Okay, the number of electrons coming out doubles if you double the intensity, and the kinetic energy we have seen is independent of the intensity, so that's why it's option B. Right, this is simple. Everyone? Yes, Nikita, Indusha. All right, good. Nikita, okay. Let's see next one. The number of photoelectrons emitted for light of frequency nu higher than threshold frequency is proportional to. Tell me. The number of photoelectrons emitted is proportional to. That means current is proportional to. Tell me. It's very simple. Yes, it's option B. Current is proportional to intensity. Right? Current is proportional to intensity. Very simple. Good. Okay, let's see next one. The figure shows a plot of photocurrent versus the anode potential for a photosensitive surface for three different radiations. Okay, three different radiations. Which one of the following is a correct statement? Which one is correct? Okay, so this is for radiation A, this is for B, this is for C. So curves A and B represent incident radiations of same frequency but different intensities. Is this one correct? That is correct, right? Stopping potential is same means frequency is same. Okay, stopping potential is same means frequency is same. Right? You need same potentials to stop the electrons. That means frequency of the light is same. Okay. So then their intensity is different. You come to know that from the positive part of this graph. Okay, when potential is positive. So if current is different means the intensity is different. So it's option A only. The curves A and B represent incident radiations of same frequency but different intensities. Okay, so it is option A. This is clear. A 5 watt source emits monochromatic light of wavelength 5000 angstrom when placed 0.5 meter away. It liberates photoelectrons from photosensitive metallic surface. When the source is moved to a distance of 1 meter, the number of photoelectrons liberated will be reduced by a factor of. Tell me. Option D. Yeah, that's correct. Correct. So number of electrons, I would say number of electrons, or you can say current, is directly proportional to intensity. Right? Current is directly proportional to intensity. So, and intensity is inversely proportional to, that I is inversely proportional to R square. So, okay, because intensity is inversely proportional to R square. So, this number of electrons would be inversely proportional to what? Distance square. Okay, distance of the source square. And then you can just put the values. So, N2 is to N1 would be equal to what? D1 is to D2, or R1 is to R2 square. Okay, inverse proportion, right? That's why this for N2 and N1, N2 in the numerator, N1 in denominator. Here you will have R1 in numerator, R2 in denominator, and you have square of that. Okay, so then you put the values. So distance initially was 0.5 meters, then it changes to 1 meter. 0.5 divided by 1 square, okay, or this is 1 by 2, 0.5 is 1 by 2, and you have square of that, so it becomes 1 by 4. So N2 therefore becomes 1/4 of N1. Okay, so it decreases by a factor of 4. That's very simple, right? Simple, not simple? Yes, Selva Kumar.
Sorry, simple only, sir.
Okay, good. Let's see next one. A photoelectric cell is illuminated by a point source of light 1 meter away. When the source is shifted to 2 meter, then, okay, this is similar to last problem, I guess. Each emitted electron carries 1/4 of the initial energy. That's not correct, right? Because you are not changing the source, you are just shifting the source. Number of electrons emitted is half the initial number. Each each emitted electron carries half the initial energy. Again, not correct. Number of electrons emitted is a quarter of the initial number. Yeah, that's correct. No, exactly similar to the last one. Okay, let's see next one. When ultraviolet rays incident on metal plate, then the photoelectric effect does not occur. When ultraviolet rays incident on metal plate, then photoelectric effect does not occur. It occurs by incidence of. It might occur by the incidence of. Question should be like this: might occur, right? There is no guarantee, no? All right, tell me what would be the answer. Photoelectric effect doesn't occur for ultraviolet rays, then it might occur for what kind of rays or waves? Tell me. Option B, X-rays. That's correct. Okay. Why? So energy of the light is not sufficient. That's why the photoelectric effect is not happening. Okay. That means frequency of the light is less than the threshold frequency. Now you need to increase the frequency. So out of these options, you need to just see which kind of light will have more frequency compared to that of ultraviolet rays. So infrared, radio and microwaves have lesser frequency. X-rays have more frequency. Okay, X-rays have more frequency, right? So that's why X-rays is the answer. Okay, because photoelectric effect will happen when frequency is greater than a threshold frequency. Okay, so that's very simple. Okay, let's see next one. A photocell is illuminated by a source of light which is placed at a distance d from the cell. If the distance becomes d by 2, the number of electrons emitted per second will become 4 times. Okay, so distance is made half, number of electrons emitted would become 4 times. That's simple. The light of frequency 1.5 times the threshold frequency is incident on a photosensitive material. What will be the photoelectric current if the frequency is halved and intensity is doubled? Light of frequency 1.5 times the threshold frequency is incident on a photosensitive material. What will be the photoelectric current if the frequency is halved and intensity is doubled? Tell me. This is from NEET 2020. It's option D. Good. Okay, so nu is equal to 1.5 times of nu naught, the threshold frequency. This is given. So if frequency is halved, that means nu prime is equal to what? It's equal to half of this 1.5 divided by 2 of nu naught. That means 0.75 of nu naught. So if it is 0.75 times of nu naught, so nu prime is less than nu naught. And if frequency is less than the threshold frequency, no photocurrent or no photoelectric emission happens, right? So that's why answer is 0. Okay, that's very simple. This is from NEET 2020. So now let us understand the Einstein's explanation of photoelectric effect. Okay, so see the Einstein's explanation of photoelectric effect. So here Einstein gave a completely different theory of light. Okay, so he says that light is made up of what? It's not made up of waves, it is made up of something like particles. Okay, so which is packets of energy, and they are called as what? They are called as photons. Photons, because photo means light, and the particles or the packets containing light, they are called as photons. Okay, then energy of each packet is equal to what? It is equal to h times nu. Nu is the frequency of light and h is the Planck's constant. Okay, h is Planck's constant. All right, then these photons, packets of energy, or you can call them particles of light. Okay, they have no mass, no rest mass. Okay, or you can just say they are massless, but they carry momentum. So photons carry some momentum and energy. Okay, then intensity of light. So this is an important concept, that intensity of light is directly proportional to the number of photons striking per unit area. Okay, so now, okay, we'll see that intensity of light is directly proportional to what? Number of photons striking per unit area. Okay, then in a collision between an electron and a photon, whole energy of photon is readily given, immediately given to an electron, and the photon vanishes. So what is photon? It's just packet of energy. Energy is given to electron. That means the photon disappears. Okay, because it's just energy. So if electron gains that energy, the photon disappears. Okay, so number of photons is not conserved in this collision, right? Okay, so now let's see how does this theory of Einstein explain the photoelectric effect. Okay, so in the photoelectric effect, we have the maximum kinetic energy of electrons. So now suppose light has some energy. Okay, so one photon strikes with one electron, then what will happen? The photon has some energy, so that energy is readily given to the electron. Now electron requires some energy to come out of metal surface. If energy of photon is greater than that energy, then electron will come out and it will also have some kinetic energy. So what can we say? That maximum kinetic energy of electron is equal to the energy given by the photon minus the work function, right? What is work function? Work function is energy required by an electron to come out of metal surface. Okay, you can say that it gains some energy, right? So what is the maximum possible kinetic energy of electron? The kinetic energy of electron is equal to the energy given by photon minus energy required by electron to come out of metal surface. Okay, kinetic energy is equal to energy given minus energy required to come out of metal surface. Whatever is the remaining energy, it is the kinetic energy of electron. Is this thing clear, everyone? Okay, good. So then maximum kinetic energy can be written as half of mv max square. It's equal to energy given by the photon is equal to h nu minus work function is denoted by letter phi naught. Okay, phi 0. All right. So now when nu is equal to nu naught, okay, when the frequency is just sufficient, it is just equal to the frequency of light is just equal to the threshold frequency. What will happen? The photocurrent just starts. That means very few electrons will gain sufficient energy, or electrons are gaining just sufficient energy to come out of metal surface. Okay, and they just come out of metal surface and then they get attracted by the anode. Okay, so they don't have their own kinetic energy. They are attracted by the anode, the positive potential on anode, right? So what you can say is the kinetic energy of the electron would be equal to 0. Okay, when nu is equal to nu naught, the kinetic energy of electrons would be equal to what? It will be equal to 0. Okay, so put that in this equation, then what do you get? So if you put nu equals to nu naught, the kinetic energy of electrons is 0. The electron just come out of metal surface and other work is done by, that means why do you get the current? Because they are attracted by the anode, positive potential or anode. Okay, so their own kinetic energy is 0, right? So this is the frequency at which photocurrent just starts. Okay, right? This thing is clear, everyone? Okay, good. So you put nu equals to nu naught, so kinetic energy becomes 0. Okay, so therefore you put 0 over here in this equation and nu naught over here. So then what do you get? 0 is equal to h nu naught minus phi naught. So then phi naught is equal to h nu naught. Okay, you get the relation between the work function and the threshold frequency. How much is the work function? Phi naught is equal to h times nu naught. Okay, good. So then you substitute that back in this equation, okay, here. So you will get half of mv max square is equal to h nu minus h nu naught, or half of mv max square is equal to h times nu minus nu naught. Okay, so this equation or we'll see that in some other form also. This is called as the Einstein's photoelectric equation. In this form also, it is known as the Einstein's photoelectric equation. You can see that's the same equation, right? So half of mv max square is equal to what? H times nu minus nu naught. Okay, or half of mv max square is equal to h nu minus phi naught. This is the Einstein's photoelectric equation. Okay, so if V naught is the stopping potential, then we know that half of mv max square is equal to ev naught. Okay, half of mv max square is equal to ev naught. So ev naught is equal to h times nu minus nu naught. Okay, h nu minus h nu 0. Then now what you can do is you can substitute that nu is equal to c by lambda, because you know c is the speed of light and it's equal to what? Frequency multiplied by wavelength, nu times lambda. Okay, so what would be nu? Nu is equal to c by lambda. You can substitute that. So you get another form of the equation, that is half of mv max square is equal to hc times 1 by lambda minus 1 by lambda naught. Okay, because sometimes they might just ask the different form of the equation. Okay, and again half of mv max square can be written as E times V naught, and it's equal to Hc times 1 by lambda minus 1 by lambda naught. Okay, so now you don't need to separately remember these equations, right? Because this is very clear. Okay, half of mv max square is equal to H times nu minus nu naught. So nu can be written as what? C by lambda. Okay, there is no problem. This is another form of the same equation. All right. So then next, suppose there is one more graph left. Now see this graph. This is the stopping potential versus frequency graph of two different metals. Okay, stopping potential versus frequency graph, and you can see these are straight lines. Okay, this is for metal A, this is for metal B. These are straight lines. They are inclined with this new axis. Okay, horizontal axis at an angle of theta, right? So now this graph can be explained by using the Einstein's equation. Okay, actually all of the graphs can be explained. So okay, let me just explain these graphs using the Einstein's photoelectric model. Okay, Einstein's photon model. Okay, so let me just explain the graphs using the Einstein's model. So see this one, first one. Einstein says that energy of the light, it is equal to what? It is equal to H times nu. Okay, so if nu is not sufficient, I mean nu is less than nu naught, it's very clear that energy of light is not sufficient, right? Because energy is directly proportional to what? It's directly proportional to frequency. So electrons are not getting the sufficient amount of energy to come out of metal surface. That's why they don't come out. That's why the current is equal to 0. Okay, so the first graph is clear. Second graph, this one. Photocurrent is directly proportional to intensity. Okay, photocurrent is directly proportional to intensity. So see here, Einstein says that intensity of light is directly proportional to number of photons striking per unit area. Okay, so if you are increasing the intensity, what does it mean? More number of photons will strike on a particular area. More photons strike, that means there will be more number of photon electron collisions. Okay, that means more photons strike, more electrons will gain sufficient energy to come out of metal surface, and that's why the current will increase. So current is directly proportional to intensity. If intensity increases, means there will be more collisions and more electrons will gain energy to come out of metal surface. Okay, so that explains the second graph. And then the third and fourth graph, so it's very simple again. The intensity, see, if you change the intensity, keep the frequency same, that means you are not changing energy per photon. Energy of all photons is same, so all electrons are gaining same amount of energy. Okay, so now therefore, see, if you increase the intensity, more number of photons will strike the electrons, so more electrons will come out, so current will increase, right? For the same frequency, if you increase the intensity, more photons are striking, more number of electrons, that's why the current is increasing. Okay, but energy per photon is same because frequency is same, and that's why electrons are gaining same amount of energy to therefore the energy required to stop the electrons is also same, and that's why the stopping potential is same. That explains this graph, right? So that's simple. Okay, and next one, when the intensity is same, means same number of photons are striking the electrons, so you gain the same current. Okay, but when frequency is different, intensity is same but the frequency is different, then if frequency is higher, energy per photon is higher, that means energy that each individual electron is gaining from the light, it is higher, so its kinetic energy would be higher. and therefore you will need to apply more potential to stop electrons, right? This thing is clear, everyone? And that's why the stopping potential will increase as you increase the frequency. And then let's see this next graph, fifth graph, okay? That is V naught versus nu, the stopping potential versus frequency. So we have seen in last graph also, the stopping potential is increases if you increase the frequency, but the graph between them is a straight line. It would be different for different metals, okay? So see, you have this equation EV naught is equal to h nu minus h nu 0, right? This is Einstein's photoelectric equation. So you can move E on other side, okay? Move E on other side, you will get V naught is equal to h nu divided by E. And what is h nu naught? It is phi naught, okay? So V naught is equal to h nu by E minus phi naught by E. So compare this with equation of a straight line y equals to mx plus c. You are plotting V naught, the stopping potential, on vertical axis, okay? Then you are plotting nu on the horizontal axis. So your y is V naught, x is nu, okay? So what would be slope of this graph? M is equal to h by e. What would be the slope of graph? M is equal to what? H by e. So no matter what kind of metal you take, the slope of this graph would be just h by e. So there might be a question in NEET that the slope of the stopping potential versus frequency graph, okay, same for all metals, same if work, same for all metals, okay? Then another option, if work function is more, the slope would be more, work function is less, the slope would be less, okay? If intensity is more, the slope is more, something like that, okay? So you need to remember that the slope would be same because h is a constant, e is a constant. That's why the slope would be a constant, because slope of this graph is h by e. This thing is clear, everyone? Okay, good. And then next is the intercept. What is intercept? Point at which x is 0, okay? This line, it will cut the y-axis. Here it is v naught axis. The line cuts over here, so that is the intercept. Now if you compare that with y equals to mx plus c, if you compare this equation, then you get intercept is equal to what? Minus phi naught divided by e. Okay, it's equal to minus phi naught upon e. So it explains this graph too, right? This is clear. So Einstein's theory explains all of the observations of photoelectric effect. Okay, good. So now let us see some numericals based on this. The number of photons per second on an average emitted by a source of monochromatic light of wavelength 600 nanometer when it delivers the power of 3.3 into 10 raised to minus 3 watt will be. Okay, so it delivers a power of 3.3 multiplied by 10 raised to minus 3 watt. We want to find out how many photons will it emit. Okay, so P is equal to what? We know it's energy emitted per unit time, right? So now energy of one photon is h nu. What would be energy of these n photons? Let's call it E prime. So E prime would be equal to n times of h nu. Okay, so power is energy by time. So energy of n photons is n times of h nu divided by your time equals to t. Okay, at t is just 1 second because power is given as energy emitted per second. So t is just 1 second, right? And then the wavelength is given. So we need to convert that nu to c by lambda. Okay, so we have n times of h nu, that is h c by lambda is equal to p, and take t equals to what? T is equal to 1 second. Put that over here. Okay, we want n. So move everything else on other side. So n is equal to, therefore you have n equals to what? P times of lambda divided by hc, and that is, what is power? 3.3 multiplied by 10 raised to minus 3. Lambda is 600 nanometer, 600 multiplied by 10 raised to minus 9, and hc, h is Planck's constant, so that is 6.64 multiplied by 10 raised to minus 34, and c is 3 into 10 raised to 8, speed of light. Okay, so here they mentioned that take Planck's constant as 6.6 into 10 raised to minus 34. Okay, so that it becomes simple for calculations. So you can divide this thing by this thing. So this will be 2, then 600 by 3 is 200, 200 by 2 is 100. So you get roughly 100 times, this is 10 raised to minus 34 plus 8 is minus 26, in numerator it is 10 raised to plus 26, plus 26 minus 9 minus 3, that is minus 12, 26 minus 12 is 14. Okay, that is 10 raised to 16. So the answer to this is 10 raised to 16. Right, this is clear. Okay, very simple question. This is from NEET 2022. Okay, all right, good. Let's see next one. This is from NEET 2023. The work function of cesium, Cs for cesium, potassium and sodium are 2.14 electron volt, 2.30 electron volt and 2.75 electron volts respectively. If incident electromagnetic radiation has an incident energy of 2.20 electron volt, which of the photosensitive surfaces may emit photoelectrons? Tell me. Yeah,
Option A.
cesium only. So what is the energy of the radiation? 2.20 electron volt. Okay, that's good. Correct. Okay, energy of light must be greater than the work function, right? What does it mean? This is h nu. H nu should be greater than h nu 0, right? This is just same condition in other words, that nu must be greater than nu 0. Okay, energy of light must be greater than work function phi naught. Okay, so work function for first one is 2.14, energy of light is 2.20 electron volts. Okay, energy is greater than this work function, but it's not greater for the second and third case, that is for potassium and sodium. Okay, so answer is CS, right? So that's correct. Very simple. Okay, simple question in last NEET. Let's see what happens this time. All right, let's see next one. The threshold frequency of photosensitive material. This is again from NEET 2022. The threshold frequency of a photosensitive material is nu naught. If the light of frequency 4 nu naught is incident on the metal, maximum kinetic energy of emitted electrons will be. Again, that's very simple. You know the formula. Ke max is equal to what? H nu minus H nu naught, right? So this Ke max is equal to H nu. What is H nu? 4 nu naught minus H nu naught. So just subtract that. So that is 3 times nu naught. That's option D. Very simple, right? Okay, let's see next one. The light rays having photons of energy 4.2 electron volt are falling on a metal surface having work function of 2.2 electron volt. The stopping potential of the surface is. Okay, the light rays having photons of energy 4.2 electron volts. This is very simple. Again, stopping potential. see, you can write EV naught, right? So it should click that which form of the photoelectric equation should we use, right? So here they are asking about stopping potential. We have kinetic energy, Ke max is equal to h nu minus h nu 0, and because they are asking about stopping potential, Ke max is equal to EV naught, right? So we should use this equation. EV naught is equal to what? H nu minus h nu 0. Put the values. Or actually we can say this is energy of photons minus phi naught. So put the values here. Okay, so this is 4.2 in electron volts minus 2.2 in electron volts. So the answer would be in electron volts. This is 2 electron volts, and that is E multiplied by, let's say, stopping potential. So that 2 electron volts, if you convert it to joules, that is 2 multiplied by charge on an electron, right? So that is E times V naught. So E gets cancelled out and you get V naught is equal to 2. V naught equals to 2 volts. Again a simple question. Okay, this is clear. Everyone? Okay, good. All right.
Sir,
Yeah, tell me.
sir, the answer is 2 volts now, sir. So it must be option C now, sir.
Oh, yeah, I just saw 2. Sorry. I just saw 2. Answer is 2 volt. That's correct. Oh, they gave one option like this, 2 electron volts. Sorry. It is a 2 volt, definitely. All right. There is one thing that to remember. So now the product of H and nu, sorry, product of H and C. So H times C is equal to 1240 nanometers. Okay, and it is equal to, sorry, what did I say? H times C is equal to 1240 EV nanometers. Okay, H times C would be equal to 1240 EV nanometers or 12,400 EV angstrom. Okay, so this thing we need to remember, the product of H times C is equal to what? It is equal to 1240 EV nanometers and it's equal to 12,400 EV angstrom units. Okay, this is very important. All right, let's see this one. The work function of photosensitive material is 4 electron volts. The longest wavelength of light that can cause photon emission from the substance is approximately. Tell me. Work function of photosensitive material is 4 electron volts. The longest wavelength of light that can cause photon emission from the substance is. So see, we know that the frequency is equal to c by lambda. That means frequency and wavelength, they are inversely proportional to each other. So if wavelength is longest, that means frequency is shortest. Okay, so longest wavelength corresponds to the threshold frequency, right? Because frequency is minimum frequency for which photoelectric emission happens is the threshold frequency, right? So if frequency is minimum, wavelength would be longest. The longest wavelength for which photoelectric emission happens is the threshold wavelength. Okay, so lambda Yeah, it's option D. Let's check. So nu naught would be equal to what? It's equal to C by lambda naught. So let's check this one. So energy work function is given as 4 eV. Okay. So phi naught is equal to 4 eV, it's given. So that is Hc by lambda naught, right? It's equal to 4 electron volts. And then you can just move that lambda naught on that side. Lambda naught is equal to, you get Hc divided by 4 electron volts. So see that expression, okay? I mean this value, we need to use it here. Otherwise, if we substitute H, we substitute C, then it takes long time to solve this. Okay, then also this thing we need to convert to joules. So we need to substitute charge of electron as an extra thing, right? Okay, so what is Hc? It's 1240. If answers are in nanometers, 1240 eV nanometers divided by 4 eV. So just divide it by that. So is it, yeah, 310, right? 310 nanometers is the answer. It's option D, correct. So this is clear. Okay, good. So you need to remember this thing. It will come handy in lot of problems. All right, let's see next one. When the light of frequency 2 nu naught, where nu naught is the threshold frequency, we know that, is incident on a metal plate, the maximum velocity of electrons emitted is nu1. Okay. When the frequency of incident radiation is increased to 5 nu naught, the maximum velocity of electrons emitted from the source plate, same plate, sorry, not source plate, same plate is nu2, V2, not nu2. The ratio of V1 to V2 is, when the light of frequency 2 nu naught, where nu naught is the threshold frequency, is incident on the metal plate, the maximum velocity of electrons emitted is V1. When the frequency of incident radiation is increased to 5 V naught, 5 nu naught, the maximum velocity of electrons emitted from the same plate is V2. The ratio of V1 to V2 is, this is a simple problem. Okay, you have half of m into V square, let's say just V, okay, in place of V max, is equal to H into nu minus nu naught. Let's use this equation twice, that's it. So you can say half of m into V1 square is equal to H times nu1 minus nu naught, and half of m into V2 square is equal to H times nu2 minus nu naught. Divide the first equation by second. So H gets cancelled, half m gets cancelled. You have V1 by V2 square is equal to nu1 minus nu naught divided by nu2 minus nu naught. And what is nu1? So it is 2 nu naught. 2 nu naught minus nu naught divided by, you have next it is 5 nu naught. 5 nu naught minus nu naught. So this thing is nu naught divided by 4 nu naught, right? Nu naught gets cancelled, so it is 1 by 4. But this is V1 by V2 square, so therefore V1 by V2 is equal to 1 by 2. Yeah, and we want the ratio only, so it is 1 by 2. So it's option A. This is clear? Okay, simple. All right, good. So let's see one more question. Photons with energy 5 electron volt are incident on a cathode. See, in photoelectric cell, the maximum energy of emitted photoelectrons is 2 electron volts. When photons of energy 6 electron volt are incident on C, no photoelectrons will reach the anode if the stopping potential of A relative to C is, tell me. Photons with energy 5 electron volt are incident on a cathode. Maximum energy of photoelectrons is 2 electron volt. When photons of energy okay, what should be the stopping potential? This is the question. Okay, tell me. Option A. Alright, let's check. Photons of energy 2 electron volt are incident. The maximum energy of emitted photoelectrons is 2 eV. So maximum energy is 2 eV, right? So you have eV naught is equal to h nu minus phi naught. Okay, so maximum energy of electrons is 2 eV, or you can say this is Ke max. So Ke max is equal to h nu minus phi naught. So this is 5. No. Energy of electrons is 2, no? Okay, so this is 2 is equal to energy of light is 5 minus phi naught. So from here you get phi naught, and phi naught is equal to what? 5 minus 2, so that is 3 electron volts. Okay, 3 electron volts. Then you substitute that. So you take second equation. When photons of energy 6 electron volts are incident, no photoelectrons will reach the anode. Okay, so EV naught, you want stopping potential, so EV naught is equal to, you have h nu minus phi naught, right? So this is 6 electron volts, so 6 minus phi naught is what? 3, so this is 3 electron volts, and therefore EV naught is equal to 3 electron volts, that is 3 times E. So stopping potential would be equal to what? 3. That's correct. No, it is minus 3 only. Stopping potential is always negative. Okay, the negative potential that we applied to the anode, okay, is called as stopping potential, and stopping potential is always negative, it's not positive. Okay, so if they say 3, if there were options like 3, 4, 5, 6, then 3 is correct, but 3 and minus 3 is there, then answer should be minus 3 only. Okay, because it's the negative potential that we applied to the anode, right? This is clear. Okay, good. So now see, we have seen some problems, but we'll see more problems based upon this, because this is an important topic. Okay, small topic but important topic, right? This is modern physics, and you might have seen, I mean, the analysis that in NEET most important topics are thermal physics, okay, that is thermal properties of matter and thermodynamics, but then they have decreased the syllabus this time. Okay, from the thermal physics, the thermal properties of matter, thermodynamics, kinetic theory of gases, this is very important. Modern physics is important. Okay, so these chapters are small, but they ask a lot of questions based on this, right? So that's why we'll see more problems based upon this thing tomorrow also. Okay, all right, so let's stop here. See you tomorrow. Okay, bye.